In the first part of today's lecture, we will look into the mechanics of a freely jointed chain as being an initial description of the mechanics of DNA. So today we're concerned with an experiment that has been done 20 years ago, where a magnetic bead has been attached to a DNA thread on one side, and on the other side the DNA was attached to a glass slide. Then this assembly has been placed in a fluid flow such that there's a drag exerted on the bead, and that in turn pulls on the DNA. Now, by changing the velocity of the flow, we can change the force. So on the y-axis here to the right, you see the log of the force, and simultaneously the position of the bead was monitored, that then reports on the mean extension of the DNA. You see at very low forces, very low flow fields, the DNA is short, and by increasing the flow field or the force, the DNA will extend to a maximum length of 32.7 micrometer, which is the completely stretched out DNA piece that we have here. Now, by zooming in and turning the graph that we saw before by 90 degrees, we obtain a force extension curve that really has been monitored in those experiments, yet here on a larger force scale. At very low forces, well below 10 piconewton, you see that the DNA is extending. Yet what we have to realize is this is not a linear Hookean-like extension, but it's non-linear. Now, if you go to higher forces, around 65 piconewton, something dramatic happens, and there's a second extension curve occurring in the DNA. Now, in today's lecture, we will are only concerned with the low force regime, and in next week's lecture, we will be concerned with the second step that we see here, which points to a transition of the structure of DNA. So our aim now is to develop a mechanical model of the DNA without looking into all the details of every atom inside of the DNA. So in that sense, we could imagine the DNA being just a cylinder of a diameter of 2 nanometer, and that can have extended lengths. Hence, we could model the DNA just as a rod, an elastic rod, that we would like to bend. Having this mechanical model and their geometry, we could ask how much energy is needed to bend such a rod to a curve that is characterized by a given radius r, capital R. So we zoom in on a small stretch along the cylinder ds and calculate the energy dE that is needed to realize that small bend. Now, very simply, that is given by some energy, and we would like to scale the energies just by kBt or half kBt. And then, knowing from last week's lecture, where we looked on the bending energy of a membrane, here we have the same effect. And we can take the same argumentation that scales like 1 divided by r squared, the radius of curvature at the given spot ds, times ds, and times a constant, which we realize just by comparing the units, has to be a length scale. Now, the parameter that we introduced here, half kBt times theta, is equal to the bending stiffness that we used in last week's lecture. The parameter we introduced here, the zeta, which is the length scale, is called the persistence length. Just for our physical interpretation, The persistence length is the small stretch for which the bending energy at given radius of curvature is equal to kVt. So we could ask now, what is the total energy if I given such a rod to bend the rod by 90 degrees? For that we have to integrate the differential, and we obtain that the energy is equal to half kVt zeta divided by r squared integral on a quarter of a circle, which leads to the energy given by pi times zeta divided by 4r kBt. We see that the energy actually can be negligibly small. For the radius of curvature, much larger than the persistence length that we defined. Hence the persistence length tells us at which length scales bending plays any role. Bending at larger length scales is irrelevant, and where bending on shorter length scales is energetically highly unfavorable. So we could view the DNA as a rod which is very stiff at short length scales and very floppy at long length scales. Now, fitting such a model to the data, and that is shown right over here, you see the force distance or extension curve, and the dots display the data. We see that the 3D elastic rod model is actually very nicely explaining our observations. And from a fit to those data, we obtain that DNA has a persistence length in the order of 50 nanometer. So on length scale of 50 nanometer, the DNA is basically a stiff rod. Now, knowing that the DNA is not just a stiff rod, but it has molecular internal structure, the model that we just made up might be not very satisfactory. So what we set out now is we would like to understand the DNA and the mechanics of DNA in a more molecular way. Well, for that we go back again to the initial data from Bustamante's lab, where the DNA was tethered to a wall, and we pull on a bead which is tethered on the other side of the DNA in order to pull on it. Now the DNA we now describe as a so-called freely jointed chain. So the DNA is made up of the nucleotides. Each nucleotide we display here as just a particle, and those particles are connected by stiff rods, yet at every particle the bending angle can be basically random. This is the so-called freely jointed chain model, and you might recall from statistical physics how to deal with this. Yet what we want to do here is an even easier model. The even easier model is that we neglect that this freely jointed chain model is a model describing a chain in 3 dimensions. We now restrict the chain being a one-dimensional object. Now in this 1D model, the angles are such that either if we connect 3 of the nucleotides together, they are stretched out. So particle 1 goes right to particle 2, goes right to particle 3, or they are non-stretched. That means I have a backbend from particle 1 to 2 to 3. And I model the configuration by just one single parameter, which I call sigma, where sigma is equal to +1 in the stretched configuration and sigma is equal to -1 in the non-stretched configuration. Now, using this definition, I can very easily write down an equation for the total extension of the DNA, given by Z is equal to L, the step from one particle to the next, times sum on all sigma I, where I runs from 1 to n, the number of nucleotides in the DNA. Now, when I pull on such a system, the energy is characterized by the work that is done. So the energy is equal to minus the extension Z times the force applied, hence is equal to minus L times the force times the sum on all sigma i's. Using this microscopic model, we now would like to evaluate the mean extension at given force and at different temperatures for that system. The method to calculate is that of statistical mechanics. So, we realize our model consists of a chain of independent particles embedded in a bath. Now, statistical mechanics tells us that we have to calculate the partition function. In this case, it's the canonical partition function. And using the partition function, we can obtain all observables that we're interested in. So let's do this. Just to remind you, beta in statistical mechanics is equal to 1 divided by kBt. Now, the partition function of such a system, Z, which depends on the number of particles n, beta, the inverse temperature, and the force, is equal to the single particle partition function, Z of 1, which now only depends on beta and the force, to the power n. That assumption is made because all particles are independent, and we know that from statistical mechanics. Now, the single particle partition function is now just the sum on the different values of sigma, which can be plus or minus 1, e to the minus beta L times sigma times f, which is nothing else like e to the minus beta LF plus e to the plus beta LF. Now, the form e to the minus x plus e to the plus x we can also express in terms of the cosine hyperbolic, and we obtain that the n-particle partition function z of n, beta, and f is equal to 1 divided by 2 to the power n cosine hyperbolic LF beta to the power n. Now, that functional form you might recall from our discussions on the paramagnet that we had in statistical physics. Now, having the partition function, it's easy to derive the mean extension per particle. So the mean extension per particle is equal to the mean total extension divided by the number of particles, which equals 1 divided by beta, the partial derivative with respect to the force of the log of the one particle partition function. Now, doing this derivative, we obtain the final result, again, which looks like the result we obtained for the paramagnet, that the mean extension per particle is given by L times the hyperbolic tangent of L times F divided by kBt. We could also invert this equation and solve for the force as a function of the extension and kBt, and we will find that this is equal to 1 divided by L inverse tangent hyperbolic of the mean extension divided by the maximum length of the DNA, which is given by n times L, times kBt. Now, this relation we could relate to the Hooke's law, where we have a relation between force and extension. And in this case, we see that the force scales with the extension, mean z, where all other factors relate to the spring constant. Now, in this particular case, we see that the spring constant scales with temperature. That is why it's called the entropic spring. So it's entropy driving the spring constant. So at high temperatures, the spring is very stiff, and at low temperature, the spring is very soft. Now, what we just derived is an expression or a prediction of these force extension curves in a more realistic, or let's say microscopic view. Yet if we plot the results of our expression that we just derived and plot those in relation to the data, we see that this 1D fully jointed chain model does not explain the data. Hence, what is needed is an extension of our model that would then finally describe the data which are the open circles in this graph. Now, this is something that we will discuss in the second part of this lecture.